we're still going to look at zeros of polynomials, but more specifically, we're going to look at the complex zeros. A nice feature of complex zeros always occur in complex conjugate pairs. All right, so what does this mean? It means that if a plus bi is a 0, then a minus bi is also a 0, or the other way around. So if you know that one complex number is a 0, then its conjugate is also a 0. Now the way that this shows up a lot of times is something like this. The directions might be find all the zeros given a 0. Given a 0. So let's say I gave you the function f of x is equal to x cubed minus 8x squared plus 22x minus 20, and you know, let's say x equals 3 minus I is a 0. Okay, so we start out with x cubed minus 8x squared plus 22x minus 20, and let's say that I know x equals minus 3i is a 0. Well, since we know that that's a 0, what we can do is we can now use this 0 to reduce the degree of this to help us to solve it. So minus 8, 22, and negative 20. Now notice I gave myself a little bit extra room because the numbers I'm going to be using here are complex numbers. Synthetic division works the same way though. You bring down the 1, you multiply, so that's going to be 1 times 3 minus I is 3 minus I. Then add down, that's negative 5 minus I. Now here's where the word gets a little bit more. For this type of multiplication, you're most likely going to need to go over to the side, negative 5 minus I, and do a little bit of side work here. So let's start distributing. That gives me negative 15 minus 3i plus 5i plus I squared. Now remember, I squared is negative 1, so that's plus 2i minus 1, or negative 16 plus 2i. So when we do this times this, we get negative 16 plus 2i. Then we add down. So that's going to be, 6 plus 2i. All right, so now we got to do 3 minus I times, a little bit more room here. So we got to do 3 minus I times 6 plus 2i and start distributing. That's going to give me 18 plus 6i minus 6i minus 2i squared. I squared is negative 1. See, those two in the middle cancel. That's negative 2 times negative 1. 18 plus 2 is 20. All right, now notice we got 0 as a remainder. If you didn't get 0 as a remainder here, you know you made a mistake because you were told that it's a 0. So we've managed to reduce this down by 1 power. So technically this is a quadratic. Now you probably don't want to write this because this is really ugly looking. Technically what do we have here? Well, these are the coefficients of, we have 1x squared plus negative 5 minus ix plus 6 plus 2i. That's what the polynomial look like with complex coefficients. Now since we haven't dealt with that before, you really don't want to try to solve that. So what we need to do is use a fact we know about complex zeros. Complex zeros always occur in conjugate pairs. So that means if x minus 3i is a solution, then x equals 3 plus I is also a 0 or a solution. So now we can do synthetic division again with these numbers as our coefficients. Now I know you're thinking, oh man, the last time was awful, and we had real numbers for that. But believe it or not, the second time you do synthetic division with a conjugate, it's always much easier than the first. So this time we're going to be using 3 plus I. You bring down the 1, and then you multiply, so that's 3 plus I. Add down, that's negative 2. Multiply negative 6 minus 2I, and 0. All right, so notice that was much easier with the second one. Okay, so these are the coefficients of the polynomial 1 degree less than what we had here. So remember, we started with x to the third. We got a 0, so that brought it down to x squared. We got another 0, so this brought it down to just x. So this is just the polynomial x minus 2. Now remember, we're trying to solve this, so x minus 2 equals 0, so we get x is equal to 2. So the zeros of this polynomial, where we were told the first one, x equals 3 minus I, means we also know x equals 3 plus I, and we found x is equal to 2. So just like last time, if you happen to be told to write this thing as a product of linear factors, we can write the original function as, move everything to one side for each one of these, x minus 3 plus I, x minus 3 minus I, and x minus 2. Now to get your lead coefficient, whatever number is right there, make sure you're looking at the lead coefficient of the original polynomial. So those are 1s, so you don't need to write that. So finding the zeros of a polynomial given a 0, just do synthetic division with the 0 that you have to lower it down to the degree that you want. Remember, if you're given a complex 0, you're actually told 2, because you also know the conjugate of a complex number is also a 0. Let's take a look at one more quick topic in this area. Something that's not quite as useful as it used to be thanks to technology, but it's called Descartes' rule of signs. Now what Descartes' rule of signs can tell you, it can tell you the possible positive and negative real zeros of the function, but it's not extremely precise. It can tell you what possibilities it can be. So what it says is the number of possible positive real zeros of a function f of x will be the number of sign changes in the terms or a power of 2 less. All right, the number of positive real zeros in a function will be the number of sign changes in the terms or a power of 2 less. Now, what does that mean? Well, we'll get to that in a second. It's pretty messy. Now, the number of possible negative real zeros, well, it's almost the same thing, of the function f of x will be the number of sign changes in f of negative x, in the terms of f of x, the terms of f of x, f of negative x, or a power of 2 less. All right, so what in the world does this mean? It's harder to write in a sentence than it is to do. It's actually very, very easy to do. So let's start out with some function f of x, and let's go 2x to the 4th minus 3x squared plus 5x minus 6. Okay, so for the possible positive real zeros, Okay, so what you do is you start with the first term and just move it over. The first term's positive, the second term is negative, so that is a sign change. From second to third, it goes from negative to positive, that's a sign change, and then from positive to negative, that's also a sign change. So in this case, there are 3 sign changes. That means there's 3 possible positive real zeros, or a power of 2 less. Now all that means is just take whatever number you get, the number of sign changes, and start counting down by 2. So it's going to be 3 or 1. Now if we count down by 2 again, it doesn't make sense because we're counting something. So we know for this polynomial, there has to be at least, there's possible 3 positive real zeros or 1 positive real zero. You're never going to have 2 positive real zeros for this. It's either going to be 3 or 1. All right, so let's take a look now at the possible negative real zeros. So what we got to do is we got to do a little bit of algebra first. Let's do f of negative x. That means take this function everywhere there's an x, put in a negative x. That's 3 times negative x squared plus 5 times negative x minus 6. And simplify. Remember, a negative to an even power is positive, and a negative to an odd power will stay negative. All right, so now if we count our sign changes, it goes from positive to negative, then it goes from negative to negative, negative to negative. So here there's only 1 sign change. Now here we can't count down anymore. So we know for this polynomial there's at least 1 positive and 1 negative real zero. And now there could be a possible as many as 3 of the positives. All right, so Descartes' rule of signs is actually a pretty easy thing to do, so it makes nice test questions. So make sure that you're trying a few of these in the homework.